Hey, what's going on, guys? CodeMonkey here. In this video I'd like to share the latest news regarding the chess engine I'm currently working on called WUKONG. So since the last video I've significantly improved the move ordering. So I finally got rid of that nasty depth limit within the question search. So from now on it goes until the better cutoff occurs within the question search, which basically allows the engine to search through the forcing lines until the composition is reached as it's intended within the question search originally. So let me just start engine playing versus itself at the depth of 5. And if you've seen the previous video where WUKONG was playing versus Toledo Nano Chess, you probably remember that it was playing really slower at the depth of 5 compared to how it goes on now, and it couldn't play at depth 6 at all because it was like slow as hell due to the really poor move ordering. But now as you can see, eventually he reaches quite pretty reasonable position in the middle game, so we have the opposite cancelling, and white has already started an attack on a king side, which is really good here, even though probably not the best ever options are considered by the engine. But it's bearing in mind that the evaluation function is really basic, and I didn't really improve it yet, so just the bare material score and the piece and the positional score tables for every piece separately, and that's kind of it, so nothing much really. So even still, it seems like it gets quite pretty nice position in the middle game, quite pretty playable, and this is what we got here. So let me enumerate the techniques I've used in order to gain the speed here, and in order to improve the move ordering basically. So what I have used, okay, it seems like, oh wow, what an interesting position we have. Well, white should win this, I really hope, unless it would be a draw. I hope it won't be a draw because, okay, sorry guys, I'm so excited to see what's gonna happen here. Okay, yeah, total winning for whites, total winning, but I'm sorry, I'm so excited, I just really want to see. Okay, so this damn reading decision again, like, didn't even let white make the black king, but doesn't matter really. So let's actually go to the source code as far as the game is now finished, so I can just show you this directly within the source code. And then I would like to share some thoughts that I came up with regarding the chess engine development principles in general. And by the way, you might wonder, like, what is this modular versus embedded stuff within the title of this video means, and you might wonder, like, what is this guy talking about? Like, the video claims that he's gonna talk about some modular versus embedded approach, but I will come to this just right in the moment, quite pretty soon basically. But before, let me just show you. Control R. I'm sorry, I just paused the recording. Not what I meant. Control F, obviously. So let's go to the very beginning of this search. Okay, here, search function. So the very first thing I've added was actually the MVV-LVA, what is known as most valuable victim, less valuable attacker heuristics, in order to order the captures. So the idea is very simple. We want to have the biggest score if less valuable attacker, like pawn, captures the most valuable victim, like queen. Well, obviously we're not capturing queens, but say queen. So this is kind of the biggest value we have in order to order the move where pawn actually takes queen. And on the contrary, obviously, if say queen would be capturing the pawn this would result the minimal score. So all the relations between the victims and between the attackers here are represented within this table. I will go deeply into explaining how exactly it works when would be implemented MVVLV within our enigmatic search algorithm playlist on this chess programming channel. But now I just want to show you how it looks like basically. And also I did add 2 killer heuristics. So the killer move which is caused by the beta cutoff within the alpha beta search of the last ply and of the one ply before the last one. So like kind of 2 killer moves are used in order to order the move appropriately, and this is used for non-capture ordering. So as far as MVVLV is used for capture, to order the capture moves, this killer move heuristics followed by the history moves, and history moves are updated when the alpha score when alpha is gaining the score. That's when the history moves score been updated. And also I've used the PV table here. If you've noticed that from now on the engine actually prints the principal variation line. It doesn't yet do it within the iterated deepening framework, but still it's already kind of interesting because the principal variation has been printed. So let me just start a new game, and I can even go for the level of 6 just to demonstrate that what I was talking about was really true. So it really kind of plays the depth of 6 at the moment quite pretty nicely. And here is the principal variation. So he supposes like he will go knight f3 and black would respond knight c6, and then he will go e2 e4, and then knight would go to f6, and then knight to c3, and then d7 d5. So this is something that would likely happen on the board basically. And again, assuming the depth of 6, which is already kind of not reachable depth for those engines that don't use move ordering at all. So this is kind of it, and it still kind of plays quite pretty nicely. Well, obviously this would last a little bit too long, so I don't really want to actually keep watching this. So let me just pause the game. Unfortunately, the stop command that is sent by the GUI to the chess engine is not yet being implemented, so we really need to wait until the engine returns basically. That's kind of it, but obviously I will implement the stop command one day. So this 4 things like MVVLV, killer moves, history moves, and extracting the principal variation moves, which are also used in order to score the moves, which I'll show you just right in a moment, is the exact improvement from the last time that actually increases the performance so much here. And before we start looking at this score move function, I just want to finally come to what the title of this video claims. So modular approach versus embedded one. And just for comparison, I would like to show you the difference between the search implementation in this my current WUKONG chess engine and one of my early previous chess engines called Chenglite. So let's go here. So where the move ordering occurs. So what we do here, we simply sort the move list in descending order. Very simple. So where the descending order is coming from, it's very simple. So we need to give every single move a particular score, and based on that score we want to put the moves in such an order that the greatest move would be the very first in the list, and the move that has the least value would be the last one within the move list. But the problem is that the move generator of WUKONG doesn't really support move scoring within the add move function, which is an example of an embedded approach. So let me just show you one of my previous engines called Changlite, and let me just find the function called add move here. Yeah, this is it. So add move is the function that is used by the move generator. So every time, let me just show you this. So here the move generator starts, and as far as we just found some sort of a move, we call this add move function. So this is literally the part of the move generator, and the problem is that what I mean by saying embedded, you remember that I've created this chess engine framework being promoted on this chess programming channel, and by the way, obviously this WUKONG chess engine is based on this framework. And the idea of the framework, as the video with the respective name claims actually, is to provide an ability for those of you guys who want to start writing search move logic from scratch without getting bothered by the by writing the move generator. This approach means that you don't really need to understand how exactly the move generator works. All you need to know about the move generator that it populates the move list that we directly are working with within our search functions, like nigamax search and the question search, obviously. So we just loop over the list of moves, of all the generated moves. We're just picking up a move. Oh my god, where do we do? Yeah, so we're just picking up a move. Well, here we do this just to evaluate that, but here we do this just in order to make the move. So just pick up the move index by the count from the move list and just do it, and that's it. So for those who has no idea like how in particular this move generator works, they don't really need to get bothered by this scoring stuff, by move scoring stuff. But so what I want to say, that if we follow the embedded approach, that means that in order to improve your search via adding the move ordering, it's not enough just to implement that. You will need to go and research like how the move generator works, kind of try to find this add move function. It might not be implemented, it might be embedded in the move generator right over in here. This is also possible. So in that case, you will need to alter the move generator itself in order to score the moves, and eventually you might even break something, so the move generator won't be working correctly anymore, and this is absolute disaster, right? So if you didn't create this move generator on your own, you definitely don't really want to alter this. So but this is how the embedded approach works. So what I want to say that obviously the embedded approach is faster because well, compare the code. We are already comparing the code, so it's faster because as far as the move is generated, it's already the score has already been assigned to it. But it's so tricky because this ply variable actually relies on the search structure. I mean the data structure that stores some search related information, like what ply now is played basically. So ply is incrementally updated within the move function, and again the same. So say this Changlite implementation, it keeps track of the ply within the make move function. That is also it's available down here. It doesn't really matter that much. I just want to show you what the embedded approach that means actually. So we have this make move function and the ply variable that actually relates to search, not really to make moves. It more like relates to search because it's used by the search, but still it is embedded. And if you don't understand where exactly the ply is being incremented and where exactly it's being decremented, it's really hard to understand like how actually to use it, because you don't really have that much experience. You can guess, but still it's not really that explicitly clear. And what I try to achieve within my chess engine framework, I try to make things as explicit as possible. And obviously, this violates the performance slightly a bit, not really that much, but slightly a bit. But in return, we have a much better readability, and also we have a modularity in terms of we can just go for writing the search function without getting bothered by the move generator and all related functions like add, move, make, move, and things like that. We can even not knowing about those functions at all. So we don't really need to know anything about them. And bearing what I've just said in mind, I'd like you guys to enjoy the beauty of the solution that I came up with regarding how to implement this modularity using this chess engine framework in order to make it easier to give an idea behind these move ordering concepts, but without a need to make you guys actually without forcing you to dive into how move generator works and trying to understand that, but instead doing everything absolutely modularly, separately from all the other parts. So search is just like one part, then we can work on separately from all the other parts. So how exactly it works basically, and again, if we just compare the code, the comparison really helps. So I just want to go back to my search stuff here. Well, let's take this Nigamax search. So we have a sort move macro here, so just search for this sort move macro. Here it is. So we just embed in the for loop within our loop of the list of moves, and here we're actually looping over the next move. So we're defining the variable called next move, and it's equal to move num is the current counter for a move list that is generated by the move list. So we just increment 1 to get literally the index of the next move. And as far as we have the index of the next move, we can already get the score of the next move as well. So this is exactly what we're doing here. So we're getting the score. So obviously we store the temporary score, but this is just the sorting algorithm. I don't really want to touch the sorting algorithm because it's not really the topic of this video. So what we really want to do here, so we want to pick up the next move score, and also we want to pick up the current move score. But this sort of logic assumes that you already do have that move score being associated with the move. And by the way, in this case, the move structure is slightly bit more complicated compared to how I've implemented this within my WUKONG engine. So here, move is not just a list of integers; it's a structure itself where we have we have two elements, kind of the move as an integer itself being encoded, obviously, and also the score. While in WUKONG we have just the bare list of just the bare array of integers, and no score is associated. No score is hard coded at the move initializing level. So the question is, like, how can we get the score for a current move in order to compare it, basically? So that's kind of it. So here we compare the score from the current move and with the score of the next move. And I understand that this macro is slightly not that readable. That's, by the way, that's the other reason why I refused using this in WUKONG. So here's how the move ordering works. Here's how the move ordering looks like in WUKONG's implementation. So this is I just separated the variables to make it a little bit more clear. So now we can actually clearly understand what exactly we need in order to order our moves. So we need to get the current move, which is move list indexed by the count, which is the outer loop here. Count is the outer loop counter variable, and then we need to then we need to get the current score for this sort of a move. So as far as we have a move, I'll get back to this just a bit later on, because not really essential at the moment. And also we need to initialize the next move. So in this case we're already using this next variable that is equal like count plus 1, so we're kind of picking up the next move within the move list in order to compare this with the current move. And then basing on that comparison, basing on the comparison of the scores, we can just swap the moves. And that's literally it. That's all what we need. And we don't even need to swap the move scores, because we don't have move scores within our moves. It's literally now just to swap moves. It's actually even a little bit faster. But obviously we take some time in order to call actually the score move position, and this is the most essential part. So when I was first implementing this morning, I realized that in order to score move, I need two pieces of duplicating code, and I wanted to place the duplication into a separate function, obviously, to clear it a bit and to make it more readable. And this is what I came up with. So let's scroll up a bit and have a look at our score move function right over in here. So here this line is very interesting, because we're not only initializing the LVA, which is the most valuable victim, least valuable attacker scores, but also assuming the structure of this LVA. You see, like, it has a 0 for the very first index within every coordinate of this two-dimensional arrays, which means that if we initialize the move that is not capture, so it would result a null in return. So this is quite pretty handy. So for the captures, we just initialize. So we're kind of killing two birds with one stone. So for the captures, we initialize the specific value of how to score the move right there within the move list. And on the other hand, you see, like, the score is not initialized, but as far as this is not a global variable, it needs to be, otherwise some sort of a segmentation fault might be encountered, or disaster like that. So so this score would be either 0 for non-captures or containing some value for captures. And then we need to distinguish between the captures and the quiet moves. And you see, like, we're creating this score variable kind of on the fly, so we're not hard-coding it within the move. And if you have a look at the logic of what we actually of how do we score, this is exactly the same logic that we're actually doing here within. Let me just find our add move function again. So it's literally the same what we're doing for LVA and for killers and for history. So absolutely the same code. But when this search related code is placed within the function that 100% relies and not relies 100% is oh my god, I forgot the word. So it's the move generator. It's the move generator function. It's the part of the move generator. It's not really. It's not really related to search at all. It's just the move generator function. So that's what I wanted to say. And here, it starts making really more sense, because we see, like, we do evaluate our score for the captures based on this MVVLV heuristics, and then in case if we have a capture, in this case we add in this 10 thousandths in order to first evaluate the captures, and then we would be evaluating all the other moves. So if then we just scoring the killer moves, which are caused by the beta cutoffs within the NingMX alpha beta function, in particular in the beta cutoffs, as already was mentioned. So this is the previous beta cutoff, and this is the beta cutoff that has occurred before the previous one. So looking up for two killer moves makes makes it possible to order moves slightly bit better, so eventually it would reverse less nodes if we use just the only killer move there. And the very last thing to score here, oh yeah, obviously I forgot that we are also scoring the history moves, which are taken where the alpha increases within the alpha beta algorithm, just the next few lines after the beta cutoff. So just kind of taking the best move from the previous iteration, and the next iteration we're using this best move as the move to kickstart search from. That's kind of it. But the most interesting thing here, that as far as we're extracting the principal variation nodes, we already have a score for a best move on a current given depth, and that's the reason why we score the principal variation moves even more than the captures, because the principal variation move is the move that is considered by the engine to be the best move anyway, so there is no reason to do the job twice, to do the work twice, so we already can just pick up this principal variation move and start searching exactly from this move. And this increases this improves the move ordering even more, so eventually we're jumping from kind of depth 4 to depth 6, which is really significantly, to be honest, because like without these techniques the chess engine is doomed to be at 4, maybe 5 depth fly, but still assuming that the question search would be limited by the depth, which is obviously violates the style of play. Sometimes it starts playing it's kind of like asymmetrical positions, which is really wrong. So obviously no one should ever use this depth limitation within the question search, but I just did that because otherwise it would just suffer from exponential growth of the captures occurring in the middle game, because there were really lots of captures there. So that's kind of it. And again, like what I want to emphasize at the very end, that this modular approach, when we don't touch the move generator at all, I mean absolutely not touching it, eventually we have the pretty decent move ordering stuff being implemented just right within the search part of our chess engine. So here our search function is like we're not touching any move generator at all, so we're doing everything just right within our search. So the scores are generated on the fly, and as far as this is the lookup, so we're not calculating anything. Obviously it takes time to call a function, put it on a stack, and just return it back from the assembly perspective, but still it's miserable compared to these benefits of having everything within the search and having it modular. And you don't really need to know how the move generator works. And like to my personal in my personal opinion or understanding, it also incredibly benefits the understanding of actually what you need to do within the particular field while developing a chess engine, while say search stuff. So when you just focus on the bare search, you can completely focus on the search and forget everything else that doesn't regard to search. And this is really interesting because like if you're bothered by the move generator, you need to think always like, okay, I need to alter my move generator slightly bit, but then it might happen that I will break it, and then my engine would eventually start playing illegal moves, and you will forget about the search, and you will be trying to say like, oh my god, where did I break my move generator? I need to make it work back, and things like that. Obviously it's not really that easy to break the move generator like this but still I hope you understand like what I mean, what I mean basically by saying that. So let me see. Okay, so here we do assign our scores, and then within the quiz and search we call this call this move order and stuff. So just put in the most in a descending order. And obviously, if we're doing this within the question search, which deals only with captures, we only get here and only assign this capture MVV LVA heuristics value, and we just ignore this part completely because we're referencing the gamma of capture flag, which only recognizes the moves where the capture flag bit is actually being set up there. So when we go to the NingaMax search, already we're doing so. This is the same piece of code, which is not really that great, these applications, but still kind of like obviously I could have made it a macro like in the previous version, but I just want to keep it more readable, and so it would be easier to understand like what's going on here. And in this case, obviously within the NingaMax search function, we deal with both captures and non-captures, and also the principal variation moves as well. So just this is the main part of the search basically. And now just to give a credit to what I've been already mentioning here. So here we update the killers when the beta cutoff occurs and fails hard. So here we update our killers. So we're setting the second killer to the value of the first killer, and the value of the first killer we're setting to the current move. So quite pretty easy. So assuming that the current killer is equal to the current move, and the next iteration it would become it would forward its value to the second killer, and they're going one by one during the search occurs basically. And here where the alpha score increases, here the alpha score increases, so we do a few things. So we do update our history moves. Well, probably, yeah, I could have put this below this, I guess. So also we store in our principal variation move, which needs a bit more explanations, but I really hope to cover it when I would be making a tutorial on how to add the principal variation into your chess engine. And the best move assigning logic, like associating the best move with the best score, is still the same, just from the previous parts, and all the same, and all the rest stuff is literally the same. Within the output, I've just added a couple of lines that now can print the principal variation, so you can see it here down below. And if you just have a look at the bare output within the console, you see like it just prints the line recognized by the Arena GUI, because this is the UCI protocol. We go for score, depth, nodes, and the principal variation. Yeah, it just I'm not sure. Probably because I drop it. Or so if I just try to run this again, this should give me a new principal variation, obviously, because as far as we can see the principal variation down here, we also need to probably after stopping the engine it won't really okay, so maybe just start a new game. Okay, and let's decrease the depth slightly a bit, so let's put it back to 5 and new game and start. So now it should really print the principal variation, this line within the console log. Well, I'm slightly bit confused why it doesn't, but this is already the Arena stuff, not the here it is. Yeah, here it is, obviously. So here we got our principal variations been printed, so everything is fine basically. Okay guys, so this is it regarding the last update. And if the last time when WUKONG was playing versus Toledo Nano Chess, that is rated for about 1224 ELO rating points according to CCRL site. I think I don't know actually how it is rated now, but I think that it's now playing like with the strength of the TSCP. And if you don't know what TSCP is, it's a very nice didactic chess engine that was developed by Tom Kerrigan. I'm not sure if I pronounced his name correctly, a long time ago in the 90s, and it served as a beginner's engine for many generations of chess programming. And beating TSCP is the great honor for everyone who is growing as a chess engine developer. So in the next video I will make I've already downloaded the TSCP and compiled this and compile it using the optimizations, so to make the best of it, so to make the most use out of it. And we're gonna watch the match where TSCP would be playing versus WUKONG. I'm not sure if the games would be different. I mean, Toledo Nano Chess always plays the same moves, so there are only 2 games that they can do at the single depth, at the same depth. But regarding TSCP, I'm not really that sure. So maybe it has some evaluation randomizations or picking some random moves from the best moves. I'm not really sure how exactly that is implemented, so we'll see basically. Well, okay guys, so this is it for this video. I hope you've got the gist concept that I was trying to deliver to your understanding, that this modular approach in the chess engine development it violates the performance slightly a bit, but it increases the readability and understanding of how the chess program actually works, and it gives and it also gives you the possibility of basically strengthen your own chess program without ever touching the mode generator, which is, to my point, which is from my perspective, is really important. So you can just take the evaluation, take the search, and just improve the stuff, and you see like your engine strength growing. That's it. No mode generator is and no reason to touch the mode generator. So this is it for this video. I hope you enjoyed it and learned something interesting out of it. So until the next time, and take care.